Hi everyone and welcome once again. In this video we are going to talk about products and equipment for restoration. Today we will first discuss pest control with the use of chemicals and conclude with the nitrogen treatment equipment, which is most useful for insect disinfestation. When we face the problem of an attack by microorganisms and insects, we must also consider the prevention system that must be put in place immediately after the healing system. Therefore, we need to think about the environment in which the work of art will be placed once treated. This means we must optimize the value of relative humidity and temperature, reduce the presence of biological pollutants, and improve both the lighting and the ventilation conditions of the environment where these objects are placed. An environment that is kept closed for long periods of time with the resulting stagnant air does in fact create a situation in which the proliferation of both microorganisms and insects can be observed. We normally refer to disinfection as a cleaning procedure for the removal of microorganisms like bacteria, while disinfestation is the most appropriate term for the removal of insects. In both the cases, we have the possibility of using either a physical intervention system or a chemical one, which relies on biocide molecules that affect the life cycle of the microorganism and that of the insects. We utilize these molecules particularly to prevent future attacks and by depositing on the surface substances that prevent the growth of both the microorganism and the insects. Today we will focus on the problem of insects. In recent years, the request for non-toxic biocides has gone up. This here is an oxymoron, a substance that is categorized as a biocide, which means that it kills life and therefore it can never be a non-toxic product. We will see how toxic these substances are and how to work safely with them. The problem of insects is particularly big in polychrome wooden statues and in wooden panels or boards. We can treat certain portions of the wooden board, for example, with substances such a mixture of wax and permethrin, which is an insecticide, in order to reduce both the hygrometric exchange and to prevent the arrival of insects that can deposit eggs in the cavities of the surfaces. And this is certainly an excellent solution, but it must be done only after a complete disinfestation. Otherwise, we risk facing a situation like that of Giotto's panel painting in Santa Maria Novella Church. In the past, this wooden panel had been treated on the back with minium in order to isolate it from the environment and to create a barrier against the arrival of new insects. However, there were already some woodworm eggs present inside the structure of the wood, and the result was that these woodworms, once they have grown, came out, not from the back that had been treated with minium, but from the front, and thus through the pictorial layers. Let's take a look to the life cycle of the woodworm. Once the egg hatches, a larva is formed, which is responsible for forming the cavities. It is the larva that eats the wood. This larva then, at a certain point of its life cycle, positions itself close to the surface of the wood and becomes pupated, and so transform itself into a pupa, which will later develop in a butterfly-like insect. Once this development is complete, the tiny butterfly will break the thin layer of wood that separates it from the surface and exit. It will then mate and go to lay eggs in the wood again. What can we do to stop this cycle? We can intervene with various substances. For example, we can use gases that affect the eggs deposited inside the wood, as well as the larvae and the pupae. And we can also use liquid systems such as the classic woodworm destroyer like the Perxil 10, which is effective on the eggs if it can reach them, and on the larvae and on the pupae, of course. These systems, however, are not effective on woodworm butterflies that are found outside the wood and that might arrive later. To eliminate those present in the environment, it will be necessary to utilize fumigants like copper smoke. However, fumigants are not effective on eggs, larvae or pupae. It is therefore absolutely useless to carry out fumigation inside a bubble or a chamber when this system has no penetration capacity inside the fibers of wood. Here we would like to talk about the toxicity of the substances in some particular situations. Take the DDT advertisement on the 1950s, for example. In the upper right image, you can see how the fleet was advertised with the phrase "more deadly than ever," a phrase that today no advertiser would ever use. Surely these substances have served to eliminate some parasites like the Anopheles mosquitoes in malaria environments. So they certainly had their utility, but they should never be applied directly on the human body as was the case in disinfection in 1950s. We can see an heroic American soldier who's being fumigated. Even during the Gulf War, this treatment went on for long periods with the application of biocides and insecticides substances directly on the skin. When we talk about toxicity, we have to keep in mind the categories of toxicity which have been reviewed in recent years. We can see how the symbols of the labeling have also changed. This skull symbol is still used for substances with greater toxicity that are now grouped together in category 1, 2 and 3. In category 4, we have the symbol of an exclamation point, which is related to the harmfulness and not to the toxicity. Categories 1 and 2 indicate substances that are lethal if absorbed. Those in category 3 are toxic if absorbed, and lastly in category 4 are all the substances that are harmful or cause irritation. In addition to these, there are the symbols related to the risk of carcinogenity, and the symbol dangerous for the environment will also be present for all insecticidal and biocidal substances. After this necessary introduction, let's take a look at the molecules that have been used in the past and we use even today. We can see how the substances highlighted in red, the most toxic one, have a low DL50 values. That is the minimum lethal dose required to cause the death of the 50% of lab animals. These substances have extremely low values, not only of DL50 but also of TLV, the threshold limit value that must not be exceeded in order to not suffer any damage. They are extremely low values, and we know that they are substances described as toxic and cancerogenic or toxic and suspected carcinogenic. These are derivatives of chlorinated benzenes, substances such as paradichlorobenzol or pentachlorophenol, or extremely toxic gases such as methyl bromide or ethylene oxide that cannot be used except by specialized companies with particular measures taken for the insulation of the environment. As far as we are concerned, we are going to use substances with toxicity we cannot say low, but at least in the medium range, such as permethrin assisted by piperonyl butoxide. If we look at the DL50 parameters of these two substances, we see how these numbers are comparable with a substance called DEET, or diethyltoluamide, which is the substance we spray or apply on our skin in the form of Autan, Odomos, or other similar products that we normally use as insecticides and repellents. Physical systems, on the other hand, are less toxic and are based on ultraviolet, infrared and microwave rays. The ultraviolet rays have the germicidal effect, and they are not used on archival material because they do not penetrate, so they are effective only on the surface, and they cause damage to paints, pigments, inks and so on. Well, infrared technology is based on the increasing of temperature, and therefore it is not suitable for objects that are sensitive to thermohygrometric changes. Even microwaves that cause evaporation of free water and even a partial increase of temperature are to be used with extreme caution. They can present problems in the presence of metal inserts, nails, pins, etc. Certainly microwaves are a valid system for other sectors. Now, we now take a look at the gaseous system other than the toxic gas system mentioned previously, and we will limit ourselves to systems based on the use of carbon dioxide and nitrogen. So systems based on carbon dioxide are certainly very efficient, but they require the supply of gas through cylinder, therefore also need proper authorization for the storage and use of this gas. On the other hand, nitrogen system works on a complete different logic. It does not rely on the toxicity of the gas, as we have seen in the other cases, and also in the case of carbon dioxide, but on the reduction of oxygen to below certain level. Without oxygen, which is the oxidizer required for breathing, all insects will die in whatever stage of their life cycle they find themselves, whether they are adults, larvae or eggs. The critical point of nitrogen treatment is the maintenance of relative humidity conditions. The use of cylinders with the flow of dry nitrogen can lead to an excessive decrease of the relative humidity and can therefore cause damage to the objects or work of art. There are oxygen absorber or capsule which when they are active develop humidity and heat. They also have a certain limitation. For example, they do not activate below 20 degrees centigrade, and if you need to disinfest large volumes, they become uneconomical. For example, to treat 1 cubic meter, you need 100 bags of this oxygen absorber. So, where do we get the nitrogen from? Let's first take a look at the composition of the atmosphere. The atmosphere we breathe in is mainly made up nitrogen, about 78%, shown by the orange area in the slide. Then we have the oxygen, which is about 21%. Oxygen is the oxidizer that we use to breathe. And then we have a percentage that is around 1%, which is made up argon, carbon dioxide and other gases. If we reduce the oxygen to below certain levels, namely below 15%, we can, for example, obtain a mixture that does not allow the ignition or the development of flames. We can still breathe in this environment, but no flames will develop. If we bring oxygen levels even lower for human this is below 10%, and for insects we'll try to reach 1% or 1.5%, we will have the death of the organism. There are two ways of working with ANOXIA. One is the controlled atmosphere and the other is the modified atmosphere. And what is the difference between the two? In the modified atmosphere we introduce nitrogen into a bubble made with a plastic material where the amount of oxygen is lower to the desired level. The bubble is then sealed and kept undisturbed for typically 3 weeks. This closed system does not allow the correction of the climatic atmospheric values, which will progressively deviate from the initial one, and so no system, whether it's a bubble, a tent or a climatic chamber, will be totally airtight. So oxygen will gradually tend to enter this environment. Of course, very efficient barrier systems such as multi-layer plastic sheets will be used, but the risk that at some point the system fails to maintain the desired value is there. Therefore, once we check them inside the bubble at the end of the treatment and find them insufficient, we will have to repeat the treatment because we would have had no guarantee that the parameters were within the desired limit during the treatment. Other system that we can use relies on controlled atmosphere. It is possible to keep the parameters under continuous control through an exchange between the sensors and probe within the system and the machine. When the parameters deviate from the desired ones, the machine activates itself and brings them back to the desired values. It is possible to record the data at equal intervals, and this also allows us to certify that the treatment was successfully completed and then the desired values were maintained throughout. It is based on this second system, the controlled atmosphere one, that Isocell and CTS have jointly developed their system. Isocell is a well-established company, a world leader in the sector of nitrogen production in various applications from food to fire prevention. And CTS is the exclusive partner of Isocell for the restoration sector, both for fixed and mobile systems. Let's take a look at the system that was developed in collaboration. The equipment you see on the right is the result of a series of prototypes and different developments that led to the system that we used today, that is the Isocell Mistral D Mobile. It is a fully integrated system that includes within a single unit the nitrogen production system, the measuring system with sensor and probes to check the values, and the humidification system in order to guarantee constant relative humidity within the bubble. It has a very high capacity of producing nitrogen through osmotic membranes that is equal to 1.6 cubic meters if the nitrogen is produced at 99.5%, and about half or 0.8 cubic meters if the purity of nitrogen is raised to 99.9%. It is the only system that has an effective safety system that monitors the concentration of oxygen not only inside the bubble but also in the external environment. In case the nitrogen leaks from the bubble, it will cause the reduction of percentage of oxygen in a work environment, and then the machine will then stop with a specific alarm and will cut off the production of nitrogen. This is a guarantee for operator in case of accidental leakage. The whole system is controlled by a software through a computer connected to the machine. The parameters of relative humidity and oxygen desired inside the bubble can be set directly on the PC that will communicate and control the bubble thanks to the data exchange between the equipment and the bubble. It is also possible to work on multiple bubbles, which means creating different environments, connected to each other with pipes. So we can build a second bubble that contains other material and will be connected with the first one. And we can thus create several bubbles connected in series. At the end of the last bubble of the chain, we will connect it to the machine and closing the circle, and so it will be analyzed continuously. It is possible to adjust both the nitrogen-oxygen concentration and the relative humidity parameters. In this way, the material inside these bubbles will be maintained with a constant and a controlled concentration of the desired values. Another possibility is to create separate bubbles in different places or room. Clearly, in this case, it will be impossible to have the automatic continuous control, and so we will call it modified atmosphere. In this case, it will be important to use a very effective barrier system and from time to time to monitor the bubble environment by moving the machine to the various bubbles room by room and connecting it to them in order to verify that the parameters inside are always the desired one, and eventually to correct these parameters by activating the unit itself. It is possible to create chambers of various sizes from 0.1 cubic meters to about 12 cubic meters or even more. But these 12 cubic meters bubble are manageable with the system ISOCEP-D Mobile that we saw earlier, while for larger rooms it will be necessary to use larger integrated systems. It is therefore possible to work with fixed chambers that allow the control of the temperature and the relative humidity. And it is also possible to create very large bubbles like the one you can see in the image below. A vast range of materials can be treated in this way, from wooden works to books, to paintings on canvas, on boards, and even without moving the paintings from their environment. So by simply detaching them from the walls and then creating bubbles in an appropriate area of the museums or in the church and so on. It is possible, for example, to create a chamber by yourself for the placement, for example, of furniture. And lastly, it is possible to do remote checking of the correct execution of disinfestation. See, in this case, here an accident has caused the bubble to break and a hole had formed on the plastic sheet, which caused the nitrogen to leak. There was thus the risk of the oxygen entering inside the bubble and disrupted the disinfestation. But the machine detected the problem remotely, activated itself automatically, and began to continuously produce a greater volume of nitrogen in order to always keep the oxygen concentration inside the bubble below 1%. In this way, it allowed the system not to lose the weeks that had already elapsed from the moment it was activated until the moment of the accident, which caused the bubble to break. We are sure of this because all data inside the bubble were recorded. You can see a series of institutions beside the numerous private firms that have purchased and used the ISOCEP-D Mobile system in their laboratories. Some other institutions, either because of budget constraints or because there are limited requirements for such a system, have preferred to go for a rental contract. And here you can see some of the institutions that has made this choice. These are European reference, therefore, not only in Italy. The system is known and used also by important institutions such as Versailles Castle in France or the Vatican Apostolic Library in the Vatican City. The ISOCEP-D Mobile system is also used outside Europe in countries like Egypt, in the Grand Egyptian Museum and at the National Museum of Egyptian Civilization in Cairo, in many museums and laboratories in Turkey, the Center of Manuscripts in Iraq, and even in China, Taiwan, Cuba, And here I'm including a short bibliography for those who want to deepen their knowledge about the problem of biological attacks from insects on specifically on work of art. Thanks for watching, and please remember to like it and subscribe to our channel and click on the bell button to receive a notification about our next videos.